All right, so we're going to take a look at limits. Limits are defined as if we let a function be defined on some open interval that contains a number a, except possibly at a itself, then we can say that the limit of f of x as x approaches a is L. Okay, so as we get closer and closer, as it approaches this a, then our function is L. Okay, it might not be L at that exact point, but as we get closer and closer to it, it's approaching L. This is kind of redundant, but this is what you're supposed to write here. This is how we write it. The limit, LIM stands for limit, as x approaches a, the little arrow kind of stands for approaches, of f of x equals L, some number L. So what this part here is showing, this graph, is that if I think about getting infinitely closer and closer to this value a here, then this function value will get closer and closer to the limit L. And that's all that's saying. So that word approaches is really important, and it's just considering getting closer and closer on both sides of the function to the actual value that we're looking at, to the a value. There's three ways that we can find the limit. The first one, numerically, we'll look at first. That basically just involves us entering numbers that are, plugging in numbers to the function that are really, really close to the x value we're looking at, getting closer and closer to it and see what's happening. And then graphically, we're going to look at the graph and see if we can tell what the limit is, what the function's approaching. And then lastly, algebraically, which we'll take a look at next week. So first, if I'm going to solve a limit numerically, basically what you're going to do is make yourself a little table like we have here. And we are first finding out the limit as x approaches 2 of 3x minus 2. Okay, so we're approaching 2 here, getting closer and closer to 2 from the left side. And then from the right side, we're getting closer and closer to 2 as well. And we're going to see what's happening to the function as we approach 2. Okay? Do we care what's happening at 2? Yes, we do care what's happening at 2. Sometimes, though, it is not defined, or there's a hole or something like that in the graph. Okay? In this particular case, this function is defined at 2. Sometimes it's not. So that's why we talk about limits. Okay. So if I plug in 1.9 to that function, I get 3.7. Plug in 1.9 here and get 3.7. If I get a little closer to 2, 1.99, that gives me 3.97. And then even closer, 1.999, so I'm almost at 2. Then I'm end up at 3.997. Okay? I actually can plug in 2, so I'm going to do it because it is defined at 2. That gives us 4. And then if I come in on the right side, I'm going to start out here because this is farthest away from 2. That's 4.3. Again, I'm plugging these numbers into the function here. 2.01 will give me 4.03. And then lastly, if I plug in 2.001, getting closer and closer to 2 from the right side, I get 4.003. So if you see what's happening here, as we approach 2 up here from the left and right, my function f of x is approaching 4. So then we say that the limit as x approaches 2 of 3x minus 2 is 4. Okay, let's check out this one. If I use this table to numerically estimate the limit, this time I'm looking at as x, the limit as x goes to infinity of 3x cubed minus x plus 1, quantity all over x plus 3. Okay, so now I'm looking, as I go to infinity, we can't plug in infinity, but we can get larger and larger and larger numbers and see what's happening to this function and make an estimation about what's happening as I head towards infinity. Okay, what is the limit as I get closer and closer to infinity? So if I plug in 10 to that function, I get 230.077. Okay, if I plug in 100, now I'm at 29,000 and some decimals. Okay, 1,000 will give you, well, it's almost 3 million, 2.999 million. 10,000 gives 29, almost 30 million. For our sake, we can just say 30 million. I didn't even take the time to plug in 100,000 because as you can see here, what's happening? The function is growing rapidly here. And at 100,000, we're gonna be huge, right? So what would we expect is happening as the function gets larger and larger? As we approach infinity, x approaches infinity, f of x is also approaching infinity, okay? So we are gonna say then the limit as x approaches infinity of this function that we're looking at is infinity, okay? Example 3, we're gonna use this table to find the limit as x approaches 0 of sine of x over x. Now for this one, this is a case where if I were to try to actually plug in 0, I would get something divided by 0, which of course is a math no-no. And so that we would call undefined at 0. But we can still look at what happens as we get closer and closer to 0 from both sides. So that's what we're gonna do here. If I plug in negative 0.1, I end up with 0.998334, okay? Get a little bit closer, negative 0.01 is 0.9999833. All right, and then negative 0.001, again, I'm plugging these x values in to this equation for x to get back my f of x. If I plug in a little bit closer to 0, negative 0.001, then I end up with 0.999999. Okay, again, it's undefined at 0. If we go on this side, furthest out here, furthest to the right is 0.1. If I plug that in, I've got 0.998334. If I plug in 0.01, 0.999983, and then a little bit closer again, getting closer and closer, approaching 0, I get 0.999999. Okay, so by the way, calculator in radian mode here for this to work out. So as I approach 0, as x approaches 0, gets closer and closer from both sides, if you look at f of x, what's happening to the function? Well, it's getting closer and closer to 1. So we would say that the limit as x approaches 0 of sine of x over x is equal to 1. The function itself is not defined at 1, but as we approach, is not defined at 0, but as we approach 0, we are approaching 1, which is what the limit is. Okay, let's take a look. Actually, I'm going to do another video for the graphs.